Good day, everyone. Today, we're diving into how operating systems have evolved over the decades. We'll compare old systems like MS-DOS with modern systems like Linux, and we're going to focus on three critical areas such as CPU scheduling, memory management, and process handling. This isn't just about what changed, it's about why these changes are necessary and how they've made our computers more efficient, secure, and user-friendly.
Let's begin with CPU scheduling, which is how the operating system decides which program gets to use the processor and when, as if it is a chef alone in the kitchen and can only cook one meal at a time. The question is, how do we decide which order to cook things in?
In older systems like MS-DOS, we used what's called non-primitive or cooperative scheduling. It works like this. When a program started running, it kept control of the CPU until it voluntarily gave it back. It's like that chef waiting for permission to move on to the next order. This sounds fine, right? The problem is, what if a program never gives up control? What if it crashes, enters an infinite loop, or it's just poorly written? The entire system freezes. You had no choice but to reboot. There was no multitasking, no running multiple programs smoothly at once.
The new way, or the primitive. Modern operating systems like Linux use primitive scheduling. Here, the operating system is in charge, and it forcefully takes the CPU away from a running program after a set time slice, usually just milliseconds, and gives another program a turn. Additionally, these systems use priority-based scheduling. Critical system tasks get higher priority while less urgent tasks wait their turn. It's like being in an emergency room where one having a heart attack will be noticed first than someone with a sprained ankle.
Imagine you're in the early 1990s. Personal computers are becoming mainstream. People want to run word processors, spreadsheets, and maybe play music simultaneously. But with the cooperative scheduling, one badly written program or even just a complex calculation could freeze your entire computer, which would lead for you to lose unsaved work and you'd have to reboot the computer. Users were literally afraid to run certain programs together. This was unsustainable as computing moved from hobbyists to businesses and everyday users who needed reliability. There are three main impacts of solving this. First, fairness and responsiveness. With preemptive scheduling, every program gets its own fair share of CPU time. Your music player keeps playing while you browse the web and download files. This means your system stays responsive even when running intensive tasks. Second, system stability. One misbehaving program can bring down the entire system. The OS can detect when a program has exceeded its time slice without yielding, mark it as unresponsive, and give you the option to kill it while everything else keeps running. This transformed computers from fragile devices into reliable tools. Third, multitasking. With modern systems, we don't just run multiple programs, but we run dozens. Your OS can run dozens or hundreds of processes simultaneously, switching between them so fast it appears they're all running at once. The trade-off? The OS becomes more complex, and there's overhead is constantly saving and restoring process states, but this overhead is measured in microseconds while system crashes cost minutes or hours.
Next up, memory management. This is about how the operating system allocates, protects, and organizes the computer's RAM. Memory is a precious, limited resource, and how we manage it makes a huge difference.
In old systems like MS-DOS running in real mode, programs had direct access to physical memory. If a program wanted a memory address 5000, it just used it. No safety checks, no protection. The problems? Any problem could accidentally overwrite another program's data or even corrupt the operating system itself. One buggy program could crash your entire system. Plus, you were stuck with about 1 MB of usable memory, a hard limit. As programs got bigger and more complex, this became a disaster.
Now, let's move to the new way, virtual memory and paging. Modern systems like Linux use virtual memory. The operating system creates an illusion that every program gets its own private virtual address space, maybe several gigabytes, even if you only have 4 gigabytes of physical RAM. But how? When a program accesses its memory, the hardware translates that virtual address to the real physical location through a page table. The program never sees the actual RAM addresses. If physical RAM fills up, the operating system uses paging. It moves less used memory pages to disk temporarily. And through this, it frees RAM for active programs. When needed, those pages come back. The program doesn't even know this is happening.
Why was this important? Protection and stability. Each program operates within a distinct memory space, ensuring that a crash in one program does not corrupt the data of another. The operating system can designate memory as read-only or non-executable, which safeguards against various types of security threats. This architecture has significantly enhanced the reliability of computers, transitioning them from a fragile state into one of the most robust dependabilities. Breaking the memory barrier. Programs are no longer limited by physical RAM. You can run applications that need more memory than you have installed. The OS juggles physical memory automatically, paging data to disk when needed. Modern computing was evolved from trusting programs to expecting potential misbehavior, prompting systems to be designed with protective measures. The introduction of virtual memory has enabled multitasking and stability in computers, such as running multiple web browser tabs and long-term server operations. While this complexity incurs some cost, it is deemed beneficial compared to the risk of crashes and security vulnerabilities.
Finally, let's talk about process handling. It is how the OS manages the complete life cycle of program from start to finish. A process is basically a program in execution with its own memory, space, resources, and state.
In MS-DOS, process management was simple, allowing only one program to run at a time until completion. There were no defined process states, limited inter-program communication, and stacked programs often required a reboot. Programs operated with minimal OS management. They loaded, executed, finished, and were done.
So the new way in process handling is lifecycle management. Modern operating systems manage processes through a lifecycle that includes several states: creation, where a new process is assigned a process ID and resources; movement through states such as ready, running, waiting, sleeping, and stop, coordinated by the OS scheduler; communication by mechanisms like pipes and sockets; and termination, during which the OS deallocates resources and reports the process's exit status to its parent. So why did this process evolve from simple to sophisticated? Process management has progressed from basic single-process models in the MS-DOS era to advanced frameworks that support multitasking and complex applications. The evolution mirrors growing computing needs for simultaneous tasks and robust servers capabilities. Modern systems now allow for true multitasking through optimized process states, hierarchies, inter-process communication, and resource limits to ensure fairness and security. This shift underscores the move from personal computing to critical infrastructure management, optimizing stability and security vital for today's digital landscape despite increased complexity and costs.
So, why did this process evolve from simple to sophisticated? So, process management has progressed from basic single process models in the Microsoft Disk operating system era to advanced frameworks that support multitasking and complex application. So, the evolution mirrors growing computing needs for simultaneous tasks and robust server capabilities. So, modern systems now allow for true multitasking through optimized process states, hierarchies, inter-process communication, and resource limits to ensure fairness and security. So, this shift underscores the move from personal computing to critical infrastructure management, optimizing stability and security vital for today's digital landscape. So, despite increased complexity and cost.
So, in conclusion, the transition from older operating systems like Microsoft Disk operating systems to modern systems such as Linux highlights a shift in focus from simplicity to robustness, security, and user experience. While older systems were straightforward yet fragile, modern systems enable stable multitasking, protected memory spaces, fair resource allocation, and system security. This complexity allows users to run multiple applications simultaneously without crashes, enhancing the overall computing experience we rely on today. So, modern operating system designers effectively manage this complexity, ensuring stability and performance for users. Thank you.